Thank you. Hi, guys. Back in the days before the internet, I used to go to bookstores to browse and see what math books they had. So among them, I found this one, which is the main source of my talk today. Here it is. You can actually find it online. It's in Spanish, but it is printed in the USSR. Here's the book. I think, no, where is it? Well, there's some parts of it, just the first page or second page, that are actually in Russian. So apparently Russians like geometry. So this is the second edition in Spanish. Mine is the first edition in Spanish from 1980. The best I could find is that the actual Russian book is from 1961. There is an English edition you can find in the, well, I don't know if you can find it, but apparently there is an English edition that came out in the 1980s. So this is my main source, the main source that I'm going to be using. The author of the book is Kostovsky. I don't know. I tried to find out whether he was still around or not. I couldn't find anything. So first, let's talk about a little bit of some of the history of this. This is what Kostovsky says. The tradition of limiting tools is old. It is very interesting that he talks about limiting tools, as in, if I could say it, as in a game, as in trying to figure this out with only those tools. Am I making sense? I don't know, but I doubt that they actually had to do this. It's like we don't have to play soccer, but we play it. And the limitation in soccer is that we cannot use our hands except the goalie, of course. So we impose on ourselves some limitations to make things a little more fun. That's my personal view. I actually don't know. Because, but Kostovsky does say that that is a tradition of limiting things on our constructions. Apparently, and this is what he says, compass and straight edge are equivalent. And they knew that back then. They also preferred the compass because they thought of it as more perfect, as a better tool. I'm going to talk about this too a little bit, very, very short. I mean, what I have to say about that is very little, but I'll say a little more in a little bit. Here's a little more history. Lorenzo Mascheroni wrote a book, Geometria del Compasso, that's Italian, and in late 1700s. And that's where he actually figured out that everything we can do with straight edge and compass can be done just with a compass. Let's say about 100 years later, this Adler proved the same theorem, the same fact, with a very, very ingenious, in a very ingenious way to prove it, including inversions. If we have time, we'll talk a little bit about that. I think this is really, really cool, the way he proved it. But it turns out that somebody else, Mr. Moore, actually did this even before Mascheroni. There was a book that was found, written by Moore, and apparently he wrote it in 1672, which is more than 100 years before Mascheroni. And that's how we arrived to the name of the theorem. The theorem says that anything that you can do with a straight edge and a compass can be done just with a compass. And that is the name of the theorem, Mascheroni, Moore-Mascheroni. Yeah, so that's just a little bit of history. A little more history. Steiner. I'm not going to try to pronounce the name of this book. He proved, remember I told you that the Greeks apparently thought that the compass and the ruler were equivalent? Well, he actually proved it in 1833. Yep. Yeah. So I was kind of looking at some of that, but I couldn't quite get how he worked it out. So you can do everything that you can do with a compass and a ruler with just the ruler with a straight edge, as long as you have a circle and a center, at the center of the circle, in the same plane of construction. Yeah, that's amazing. I think that would be a next topic, perhaps, to look at. And then there's other geometries. Lobachevsky is the one who came up with non-Euclidean geometries. And there's been some people, mostly Russians, who have studied non-Euclidean geometry. Actually, those people were studying constructions in non-Euclidean geometry. Yeah. So that is just a little bit of history about this. Before we start, we have to talk about what a compass is and what a compass can do. Most people think of a compass as something like this that you can open, and then you can keep at the same length, at the same angle, even if you move it. Technically speaking, you are not necessarily supposed to have a compass like that. You have what is called a collapsible compass that you can draw a circle with, but then as soon as you lift the compass, it collapses. It loses its angle, and you cannot reproduce it unless you open it to 2 points on the plane and then to draw a new circle. But as soon as you lift it, it collapses. So one question we have is, and some people ask this question, can we work with a collapsible? Can we do everything we can do with a compass as with a collapsible compass? And the answer is yes, absolutely. In fact, that is proposition number 2 in Euclid's book number 1. And I can show you how to do that. So if you don't, that is what I'm going to do next. If you have a non-collapsible compass, okay, yeah, and you have this distance, this is a distance, and you want to transfer it to this point. If you have a non-collapsible compass, that's not difficult. All you do is measure. By the way, this is dry, so I'm not going to be able to draw with that, and I don't need it anyway, so because after this little demonstration, I don't need it anymore. Okay, so you open it to that, you transfer it here, and you can put it anywhere you want, like at this angle. So this distance got transferred to here. Am I making sense so far? Okay. Can I do that with a collapsible compass? And the answer is yes. Yes. I work with a lot of compasses. In preparation to this talk, I tried to use this, which doesn't work very well because there's not enough friction here. I tried this other one, but it doesn't work too well because this is too thick. It looks nice, but it's too thick. Mr. Dersch let me use his. This is his. I really like it. It's one of the best ones. So I'm going to try this. I'm going to try to show you how to do this. So collapsible means that as soon as I'm finished with an arc, I let go, and there's no way to get it back unless I measure again with 2 points on the graph. That's what we mean by collapsible. So the first thing we do with this is, we need to draw an arc here, an arc here. Yeah, you gotta practice this. This is fun, by the way. It's something that I advise you to do. You have nothing better to do on weekends. There. So those 2 points, you would agree, are exactly in the middle between those 2 points. Does that make sense? In fact, this is an equilateral triangle, and this is another equilateral triangle. Yep. So now what I need to do is move this distance. Again, oh, this is a little short, but it will do. Yeah, it's almost on the tip. I need to move it here anywhere. Yeah, I'll just do that. And then I need to measure this distance here and transfer it there. Notice that I'm not lifting my left hand, which is the pivoting point. As soon as I lift it, then the compass collapses. So there, I have transferred it. This distance is the same as, doesn't look like it, does it? Let me try it one more time, just to, because this has to be, the only problem with this is that you gotta be fairly precise. Oh, I gotta use this distance again. 1, 2. And this is like a video game. You start memorizing, no, this distance. Your sequences of moves. 1, yeah, that's better. And then I need this, and there, that's better. So this distance is equivalent to this distance. We have successfully transferred it from one side to the other, because essentially what's going on is that from this point to here, we have the same distance since we use this point for an arch, or an arc here. And then we have from this point to this point the same distance. I don't know if you want me to show you more, or this is sufficient. Yep. Yeah. So anyway, what this allows us to do is to transfer distances. So I don't need necessarily a collapsible compass anymore because I can transfer any distance. That's what we can do. Yeah. Let's move on to the next slide here. Compass geometry. Well, with compasses, I cannot draw a straight line. I can only draw circles. So what do we mean by a straight line if we don't have a straight edge? We need a definition, and this is the definition, or the convention. We say that a straight line has been completely finished if 2 points on the line have been drawn. So as soon as we see those 2 points, we realize there is a line through them, even though we don't actually draw the line. If you see 2 points like that one and that one, then there's a line through them, even though we don't draw it. Yeah. 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 You can ask questions, of course, or interrupt anytime you want to. So what do we need to draw things on, with a straight edge and a compass? We need to be able to do these 5 fundamental constructions. Draw a line through 2 points. Draw a circle with a center and a given radius. The intersection points of 2 given circles. And we need to determine the intersection points of a straight line and a circle, and also the intersection points of two straight lines. Let's see. Let me just put down 1, 2, 3, 4, 5. Which ones can we do with compass alone immediately? Number 2, we can draw a circle. Certainly, if you have a compass, you can draw a circle. And which other one? There's one more you can do immediately with just the compass, no straight edge. Which one? 3, yeah. You can certainly, if this is one circle, let me put a center, and this radius, there's 1. another center, any radius, there is one. So I don't need a straight edge to find the intersection points of two circles. There they are. That's all I need. So 2 and 3 are immediate. 1, well, we cannot draw a straight line, but we can draw many points on the straight line if we wanted to. We are going to substitute 1 with another proposition that says that we can construct any number of points on the line. And 4 and 5 definitely have to be substituted. Okay. To do that, we are going to show 7 constructions. Yep. Again, we could do 2 and 3, so that's not a problem. We need to be able to do 1, 4, and 5. So the constructions I'm going to show you are such that after doing A, C, and G, we will be able to do 5, this last one. This is very, very interesting, I think. After doing A, we can do, A and E, we can do 1. A, D, and F, after doing those 2, then we can intersect 2 circles like that. No. A circle and a straight line. Yeah. I'll show you. So here are the actual statements, A through G, given a line AB and a point C. We're going to construct a point that is symmetric to the point across the line. Let me show you how we do that with a ruler. I forgot to check. Is there a ruler here? Oh, there it is. Yep. There's 2 rulers. Okay. One of the things I want to do is compare and contrast straight edge and compass versus just compass. Okay, so you have a straight line. Draw any point. Can we draw one that is symmetric to this point across the line? And the answer is, of course. Just pick any random point. Draw an arch like so. Another random point. Draw an arch. This point is perfectly symmetric to that one. In fact, if you draw the vertical line, the line joining them, there's a 90-degree angle here, a perfect 90-degree angle. Can we do that when there is no line, or if the point is outside the line? Well, this line is supposed to be as long as we want it to be. We can extend it as far as we can go. So let me show you. Yeah. Just want to make sure I have enough room. Yeah, let's say this is a line. That's a line. Do you see the line? There's a line, and then there's a point that is outside the line. My goal is to try to draw a point that is symmetric to this point across the line down here with just the compass. Draw this distance, and then draw this distance. Actually, it is the same method that we just used. This point is perpendicular. That line across is perpendicular to this line. And this point is the same distance from the line as this point is. It does help to draw perhaps the line that is supposed to be there. And the line, so a dotted line means the line is not necessarily part of the construction, but it is there. There. So there's a 90-degree angle here, and we can do that. So there's number 1. This is an interesting one to compare straight edge and compass versus just compass. By the way, anyone who wants a copy of my presentation will be able to get one. Just send me an email. I'll give you my email at the end. But not like you want to have, not like you really wanted it, but necessarily. But like, why would I want that? Okay. So let's say you have a segment. This is just a line, a segment A there. And you want to produce a segment of length 2A. Okay, so I measure A. Now, we did say that we can transfer distances, correct? So I can just do that. Actually, I don't have to. I could have just done this. Same thing. So that is 2A. 3A, well, do the same thing again. So that is 3A, etc. So with a straight edge and a compass, it is easy. How about if you don't have the straight edge? I'll do it here. I'm going to erase this. Yeah. So again, I draw. It takes a little while to get my foot in here, but semicircle, a little more than semicircle, because I don't know exactly how much a semicircle is. I don't have the line to cut it. But then you take this distance, and you go 1, 2, 3. This point is exactly opposite to this one across this point. Now I got 2A. This was A. I got 2A in a straight line. Well, once you got 2A, you can do 3A because you just redo the same thing over. So I'm just going to show you real quick how to get started. So again, you measure. Yeah, and I don't know where it ends because there's no straight line. Well, I can sort of see it because I erased it, but I don't see it. So then again, you start measuring your sixth of, because every time you do, you can build a 60-degree angle very easily. What we did here is draw an equilateral triangle. So 60, 60, 60. Another one here. Another one here. And so now we just keep going, because 60 plus 60 plus 60 is 180. So that's essentially what we did. So that's how we can produce segments that are twice as long, 3 times as long. Given lengths A, B, and C, find the fourth proportional. That's a very, very neat result. I'm going to do it here. First, with a ruler. So let's say this is A, B, I don't know, C, about there. Let me make A little longer there. A, B, C. So if you have the proportion A over B, I want to have a fourth element here, which we're going to call X, so that it is proportional to A over B. Now, with a straight edge and a compass, that's not too difficult. Let me remember. Oh, yeah. So first, I'm just going to draw a line first. There. Draw A, measure A, which we can transfer. That is A. This length is A. Measure B. So that is A, and the short one is B. The long, from the top to the bottom, is A. From the top to here is B. Then do C. C is the long one. Yep. So you do this, and you put it anywhere here. So again, I'm transferring C down here. Now, this time I'm contrasting. I'm using the ruler, the straight edge. By the way, straight edge means that I cannot measure other than with the compass. There. Then I can close this triangle. oh, I need to do a construction that I'm just going to, because this is not really the talk. This is not straight edge and compass. This is just compass. I'm going to wing the next step. I'm just going to, do you know what to do next to get the proportion correct? The x, by any chance? Similar triangles? You guys remember? Yes. I need to draw a parallel, which is a construction itself. So I'm just going to pretend I know how to do parallels. Yeah, I'm just going to eyeball it. There. So this would be x. That will do the job. Again, I did not quite show you how to do the parallel because we don't need it with just the compass. The compass makes this a lot easier, as you will see. Okay, so I'm going to show you with the compass only how to get x. So same thing, I need a center. I always forget to draw my center. I draw my arc and then I forget what the center is. So just draw a long arc. Don't lose the center. There it is. Then B, there, B, on the same center. Then I need one point to get started here. Let's say this point. C, I measure C here. And then you can take any distance, but I'm going to keep my C and do this. Oops, there's my C. I'm going to do this. And then I'm going to make another cut through this smaller circle here. Well, guess what? This is, from here to here is my x. It was a lot easier and faster. I'm going to show you why. Okay, so I'm done with the construction. I'm just going to show you more or less why. Okay, so here's one length. Remember what length this was? ABC, which one? A, correct. So draw A again here. And what is this length? Try again. C. Oops. Well, this length would be x, just by the same argument over there. But this is the same x just shifted. I thought this was, when I saw that, I was like, whoa, that's so cool. Now, this distance is about the same distance that we would have gotten here. So that is the x. So we can do this. Oh, there's one question or one issue that could arise. What if C was really large? I could draw C if C did not exceed the diameter of the circle. The diameter of the circle is 2C, rather 2A. So if C is too large, this doesn't work. That's actually easy to fix. Multiply the radius multiply A. Instead of using A over B, if C is too big, then change A, with 2A. If it doesn't work, then use 3A. And we know how to extend a segment. So, and then find your x. The x we're going to find has to be multiplied by the same amount, has to be added, with itself by the same times, and you will get the proportion you're looking for. So I'm not going to go into that because that can take a little while. But the neat thing about the constructions is that they thought about everything. Even if the constructions are not as neat as this one, you can still work with the numbers, with the constructions. Okay, So we got A, B, C. That was a neat one. Splitting, that one is a difficult one. That is a difficult one. I'll show you how to do it with a straight edge first. With a straight edge, it is kind of not too bad. Yeah, we're finished with this, so we can erase. So if you have your center here, let's say you have any random arc. By the way, if you lose your center, you can find it just with a compass. That's another construction. That is an advanced construction. But you can find it, even if you have just one arc of the circle. Yeah. I looked at it and I thought, we don't have enough time to do that. But you can find the center. If we have a ruler, a straight edge, that's not a problem. Just take this guy, do an arch, take this other distance, which is the same distance, do another arch. Then what do you think I'm going to do if I can use a straight edge? Yep, so draw the, see, that's helping a lot because that's saving us tons of time. Yep. So there's the splitting point. Yeah, that gives us a lot of advantage. The straight edge and the compass together can do things really, really well. The compass alone can do some things really well, but some other things are not as good. Okay, so we're going to try to do this without the straight edge. This is actually working okay because of the angle. Most people can see. I was afraid I was going to stand right in front of the picture, and that wasn't going to work too well. Okay, so there's the center. Anywhere. There is an arch here. I don't want to make it too long. There. And we want to split through the center. We want to split the arc in two halves. Okay, so first, see, I take this measurement, and then draw a circle. I don't need the whole circle. That's all I need for now. Then take the radius, and cut through here. And I'm just going to making sure that my radius is accurate, and cut through here. By the way, I'm going to start labeling my points because this gets just a little bit complicated, not too much. This is A, B, C, D. Then I'm going to take CB, John. So I'm going to, these knots are nothing. It's just, that was the first thing I found in my garage. So there. So then I do B, C, draw an arch here, AD, yep. Let's label this as E. Okay. Oh, then take the distance, this is O. Take the distance OE and transfer it to C. OE. See, if I lose it, it's okay because I'm working with a collapsible compass. And transfer it to D. That is the half way. Now, how does that happen? There's some parallelograms going on. There's some formulas going on, but it's I don't know. When I saw that, I was like, no way. And yeah. Oh, and there's more to this. If you take EO and go this way, and again, EO, and go this way, guess what that point is? Yes, it is. This point is splitting the other arc. Am I making sense? Because this is a circle. We're splitting AB, and this point splits AB, but the other way. Yep.
Would not be the distance from O to M and O to your new one the same distance?
Yes. Yes. Now I lost. Oh, there it is. Yep. Yep, exactly the same distance. So, whoa. Split an arc in half. That's, I don't know. This one is not too bad. Construct an arbitrary finite number of points on a line. I'm looking for the eraser. Apparently there's only one. I'm going to do this one on the side here. And anyway, so 2 points. I want to draw more points on this line. There's a line right there, and I want to draw more points. So find a midpoint above the 2 points. I actually wanted more than that. One above there, and one below. So take this distance and go up and down. And then take any length you want and start drawing points, arcs, from here and from there. So there is one. There's one. There's 1 point on the same line as those 2 points. So those 3 points are collinear. And you can do that anywhere. So you can go as far as you want to. Yeah. So I'm taking this, any arbitrary distance. Now I can go long. And I do this. And as long as I keep the same distance from here, this point is collinear with those 3. And you can keep doing that on the left and on the right. Yeah. So you can, even though we don't have an actual solid line, you can draw as many points as you want on it. Okay. Now we go to the actual constructions that substitute the fundamental constructions we could do with straight edge and compass. Okay, so these are the big ones. The intersection points of a given circle and a straight line. First, I'm going to show you how to do that with straight edge and a compass. Okay, so the center, do I need a center for this one? No. So, mark, yeah, okay, I'll mark it, sure. So, well, I'm going to use the straight edge, so this is easy with straight edge. So let's say this is a circle. Well, it's not the full circle, but some of it. And then you have a line. Let me go down a little farther. There. Can we find the points of intersection? Well, they're pretty obvious. There is one and there's the other one. So the challenge is, what if we don't have the actual ruler? Because the ruler is the one that did the job. So pretend you started with points back here. How do you find those 2 points? Well, the ruler tells you. What if we don't have that? Is it okay if I erase this? Okay. Now here I definitely have to keep my center. I need it. So pretend you got a circle and a line, but I cannot use the ruler anymore. Say the line is, let me go a little farther. There's my line. How do I find where they intersect? Close, yes. Oh, but then you are, see, we have to be precise. Yeah, we can approximate, yes, but we want to be right on it. Yes, yes. Yeah, that's a good point. Yeah. So we do know how to draw a point that is symmetric to this line. We did that. That was A. So I do that now here. There. And then I draw another arc here. This point is symmetric to this point across this line. Now take this radius and draw another circle here with the same radius. This point and that point are the intersection points of that line and the original circle. So that's not too bad. So now we can intersect straight lines and circles, but now just with a compass. Just with a compass. This one. Yes. That one is not going to be. So first I'm going to show you how we do that with a straight edge. You got two lines. Say that one and actually this line and this line. So there's one line and that line. If you have a straight edge, can you find the intersection point? No problem. Oops. Well, there's my line, my other line, and of course the intersection point is where they cross. That's pretty clear. Can we do that with just this? And the answer is yes. Let me show you how. I'm going to try to start here and hope for the best. So there is the line AB, there, C, and D. And we want to find the point where they intersect without using a straight edge. It's going to be, I can eyeball it somewhere in here, but to locate the precise point of intersection is not trivial. So first, I'm going to find symmetric points to C and D across across AB. So I'm going to do this. I'm going to do this. Then I'm going to start with B, measuring C. And do this. And measuring from B, the distance to D. And we're going to get that. I think I moved my hand a little bit, but hopefully I'm okay. C prime, D prime. Okay. What I'm going to do is transfer a distance, this distance, from C to C prime.
to here. Yep. And transfer from C to D down here. And we're going to call this E. Yeah. It turns out this point is directly below those two. Well, I shouldn't say that, because I don't know what below. They are collinear. E is collinear to D and D prime. And the reason is because we have a parallelogram. This distance got transferred to this distance. And this distance, which is the same as this distance because of the symmetry, got transferred down here. So we do have a parallelogram C, C prime, D prime, E. There's our parallelogram. So yeah, so this is parallel to that, and consequently, that's parallel to this. Parallel. We used parallelism in when we were trying to do C. Remember what it was for? Well, it was for similar triangles and to do the ratio. Well, we're going to do that here. It turns out that the point of intersection has the same, well, let me put it this way. DE divided by DD prime, DD prime, is equal to CD divided by the distance from D to the point of intersection. I'm just going to call it X, length X. So if I can find the fourth proportional to those three numbers, then we're set. But we know how to do that. I'm going to erase this first. See, that's why we need the other constructions, so we can get to this point. I'm going to draw a circle here. Oh, barnacles. I forgot to put my center. Let me try again. That's about right. Okay. Then DD prime the center is not necessary anymore. CD, oh, I do need a point here. There. And then I can use any distance. I'm just going to stick with the same distance. And this is the fourth proportional. This is my X, this distance. So I can transfer this distance. I'm going to use my left hand instead because of my drawing. I'm nervous because this has got to be pretty precise. All right, I'm going to transfer that here and there. That is, well, it's off just a little bit, but that is the intersection point between those two lines, this line CD and AB, precisely. So we can cross two lines. Now, we could do the same if you have 2 points like so and 2 points up here. It's almost the same construction. The only reason why I'm doing this construction is because with the other construction, I have to use bigger circles. The proportions don't work as nicely as with this one. But we can cross, yeah. And the reason is because, remember the parallelogram we had here? There's a parallelogram there. So these two lines are parallel. Yeah. And I'm going to use the other parallelogram instead. Yeah. well, I'm just going to leave it like that. So, but yes, that is the point of intersection. So, we have shown the fundamental theorem. Any construction that can be done with compass and straight edge can also be done with just the compass alone. You don't need the straight edge, because everything that was fundamentally basic with the straight edge and compass, now we can do with just the compass. Oh, we still have time for more. There is some neat constructions that we can do. So draw perpendicular to a segment AB. I'm ready to do that one. I'm not ready to do the other ones. I don't want to spend time doing that, but it's kind of neat how this is done. It's very, actually not it doesn't take too much time. But I want to show you some other things, or tell you some other things, so that's why we're going to skip it. It's very, very fun to see the constructions that can be done, like this one. Given a segment AB, we can draw half of the square root of 1, that length. So if AB is 1, if the length AB is 1, then we can draw half of 1, half of the square root of 2, half of the square root of 3, half of the square root of 4, all the way through 25. And here's the picture. Here's the construction. And of course, I didn't do that. That's from the book. But that is the construction. And actually, you see all those numbers in there. So this may mean something like the square root of 3. This may mean, well, half of square root of 3. And I'm just making this up because I don't know which ones actually are the ones that are used. But this could be a half of square root of 7, and so forth. All of them are there. So it can get very, very complicated. But it's fun at the same time. I think it's neat to do this. Kostovsky says that he thinks that the constructions are very elegant, very neat. Once you start working on this, they seem not as messy. I don't know about you, but I think less is many times better. So if you just see the dots, that looks more elegant, I guess, to some people. And he asked, how could this be done? I mean, how did they think of it? We have I'm just going to tell you the idea of a conversion. Conversion is another way to do this. Let me very quickly talk about symmetry. I'm going to erase this. We don't need that anymore. So symmetry. We have different kinds of symmetry, as you know. So a heart is symmetric because any point on the left has a corresponding point on the, I said left, I meant right, has a corresponding point on the left at the same distance at a 90-degree angle. And the same thing happens with every point on the left or on the right. That's symmetry with respect to a straight line. But there is symmetry with respect to a point. So the letter S, like that, is symmetric across a point because every point here has a friend on the opposite side of the point, across this way. This one has a friend here, and so forth. Every point has a corresponding point across the point. So that is symmetric with respect to a point. And you guys have seen symmetry with respect to a plane. So if you have a mirror and you got a stick person, right hand up, the image has his or her left hand up. So that's symmetry across a plane. Symmetry across a line, symmetry across a dot or point, symmetry across a plane. And then there's a new, I call this symmetry, but in mathematics it is called inversion. Inversion. If you have a circle and you got a point far, well, it doesn't matter, a point outside the circle, you can map this point into a point here. That is true for every point outside the circle. And it's easy. Whatever the distance is from here to here, do the reciprocal. Oh, this is a circle of radius 1, although you can do any circle, but radius 1 works well. So if this is 3, map this point in the same direction to 1/3. Something neat happens with this. Every straight line, guess what? Turns into a circle. Every straight line turns into a circle under inversion. Well, there's only one exception. That's why I have this almost. But I did very, very tiny, so. There's only one line you cannot invert and have a circle, the one that goes through the origin. That one you cannot, because that one inverts into itself. But any other line inverts into a circle. So if you have another line, let's see, closer, then that is another circle like so. And if you intersect two lines, then they also intersect. This is going to be difficult, but I'm going to try. They kind of do this. They intersect at the origin, which is infinity, and they also intersect at 2 points. And the angles are preserved. Inversions are very, very neat transformations. Anyway, why is this relevant to compass only? Anything you do with straight edge, oh, I forgot to tell you one more thing. In addition, any circle is mapped into a circle also inside this unit circle. So circles and straight lines both become circles. Well, any construction you want to do here, map it into here, and then map it back, and you get your construction just with compass. That's another talk. That's another hour of explaining how or why. But that's I think, neat. And you should ask, well, fine, but how do I transfer points from here to here? You can do that just with a compass also. So this could work, and it does work. I think it's more complicated to do that, but it does work. Let me see. Just curious facts. This guy was, I'm going to skip this one. Another curious fact. I was looking at the book, the Euclid's book. This is my copy, although it has a lot of footnotes. And then I started checking which of the propositions are constructions and which are not necessarily constructions. They are if-then propositions. And this is my list. 22 shows up twice because 22 is both a construction and a statement, if-then statement. Why do you think this is there? I mean, this is bold. Proposition 47 and 48. Those are Pythagoras' theorem together. Well, 47 is one direction, 48 is the other direction of Pythagoras' theorem. So it's kind of neat to compare how Euclid did some constructions versus just with compass. And going back to the beginning of the talk, I think that was a limitation they wanted to impose on themselves. That's my personal view. I think they just said, just the compass might be too difficult, just the straight edge might be too difficult. This is about the right balance. Let's do straight edge. Who knows, it might follow historical reasons. I don't know. But nonetheless, it is just a limitation that was imposed on themselves. Yeah. Maybe people before Euclid only used straight edge and compass, and Euclid kept it that way. That's it. Thank you guys for listening.